angles.
Are we live?
Like, good thing that we had that conversation before.
The last time I gave you a few homework problems?
Yes, you did.
51 maybe?
Yeah.
Yeah.
Any questions?
27A.
27A.
I don't like these. I can't get them.
The long ones?
The arc stuff.
Oh, the arc
Like, I don't
stuff.
even know like what it's asking.
I'm not sure if I ever do this.
Yeah, I forgot.
Which is fair, it's been a while. Now, the arc in front, let me say it this way. When we normally talk about, let's talk about the cosine function. We take an angle, let me go sine. You put in an angle, you get out a ratio. The sine of 30 is a half. Okay, that's the way that function works, right? You put in the domain are angles, the range are ratios. Now, the arc in front does the exact opposite. It's what's called the inverse function. So it reverses the role of x's and y's. In this case, it reverses the roles of the angles and the ratios. So when we talk about the arc sine, another way to write that is sine inverse. What we're talking about is the function that takes a ratio and produces an angle. Now, that means that this 3/4 is going into an arc sine function. Then this 3/4 is a ratio. Well, what type of ratio is this? This 3/4, since it's in an arc sine, this is a ratio. Normally, remember, when you have a sine function, whatever follows the sine is an angle. But whatever follows the arc sine is a ratio. And not just any ratio, but in the case of arc sine, this is a ratio of opposite over hypotenuse. So, we have arc sine 3/4, this is a ratio, and specifically a ratio of opposite over hypotenuse. Now, I think we can draw a triangle with that relationship. I'm just going to take a generic triangle. It's got to be a right triangle so that we can use sine, cosine, and tangent. And there's my angle. I want my sine to be 3/4. There we go. Now, we have our triangle. The arc sine gave us our triangle. Now, we're asked to take the cosine of that angle. Well, here's that angle, and we need to take its cosine. So we need the adjacent over the hypotenuse. We know the answer is something over 4. We just need to know what it is over 4. And we can find that working backwards with the fag, right? We can go a squared plus 3 squared equals 4 squared. What's that? A squared plus 9 equals 16. A squared equals 7. So that's root 7. There's your answer. So the big distinction between the sine and the arc sine is what is put into the function. The sine you put in an angle, the arc sine you put in a ratio. And if that distinction can be clearly made, then you can take arc sine information and make a triangle. You could take sine information and make a ratio. Good. Other questions? Did you guys, 17 and 18, both nailed? Sweet. Yesterday was well worth it then. Well worth it. much. So, let's remind ourselves where we stopped due to the time yesterday. In 51. If you see a log with no base written, the base is assumed to be 10. If you see an ln instead of a log, the base is assumed to be e. And all you need to know is that e is this number, like 2.718 something. It's less than 3, it's more than 2. You don't have to know exactly what the number is, but to know that it's just some number, and it's a magic number, calculus produces it. Okay. Here's a question. Let me just jump into a question and let me show you how we can approach this. So find log 2.4. Now we want to know what log 2.4 is. So basically, we want to know what that is. Think about it like this way. If I make it an algebraic statement, I'm saying the unknown is that guy. Does that make sense? If I want to know what this is, he's my unknown. Well, you could rewrite that and say 10 to the x equals 2.4. If you raise 10 to some power, you'll get 2.4. Now, if you could magically produce what that power is, you would be a superhero. But we're not asked to be superheroes. That's what our calculators are for. So if you pull out your calculator, you will notice that your calculator has a log button. And when you push the log button, it will not give you a spot for a base. When you push the log button on your calculator, it's assuming base 10. So if you go into your calculator and say log 2.4, that will give you the power that 10 would have to be raised to make 2.4. And what is that power? 0.38? Does that make sense? Because 10 to the first power would be 10. 10 to the 0 power would be 1. It's got to be somewhere in between. So I think we're good. What if we wanted to find ln 2.4? If you don't know what something is, just say, okay, that's my unknown. Make this an exponential statement. The base is e. So we say e to some power is 2.4. If you know that e is around 2.7, then you know that that power's got to be around 1. But now, since we're not magicians with numbers and can come up with that x, we can let the calculator do the work for us. And say ln 2.4, okay, so x is 0.88. Does that make sense? If e is 2.7, then 2.4 is a little less than 1 copy of e. Good so far? Okay. Okay? Slightly harder questions. Write 24,000 as a power of 10. Whoa. Now, you can imagine, if you take 10 times itself a certain number of times, you could make 24,000. Here's what this looks like. We want to write 24,000 as a power of 10. Are you comfortable with the translation I just put up there? Now, if you had magic skills, you could figure out exactly what that x was. Do you have the magic skills? No. But, what if we took this in exponential form and rewrote it in logarithmic form? Maybe it would simplify. If I rewrote it in logarithmic form, it would be log base 10 of 24,000 equals x. Aha! So the x, the unknown, is just log base 10 of 24,000. But you have a log base 10 button on your calculator. So if you just do the log of 24,000, you can find out what the x needs to be. Hopefully this x is more than 1, because you're going to need many 10s multiplied by each other to make 24,000. How many 10s do you have to multiply by each other? 4.38. So 10 to the 4.38 power is 24,000. Test it. Just try it out just to be, you know, kosher with yourself. Put in your calculator 10 with the little raised 2 sign, 4.38. Just plop that in your calculator just to be sure that we're not, you know, full of hocus pocus. Does it come out as 24,000?
23,980.
Yeah, we chopped out a couple decimals. So 23,900 right there. Okay? Let's write 24,000 as a power of e. So a power of e, I need some power of e to be 24,000. So 24,000 is some power of e, e to the x. Do you magically know what that x is? No, and if you do, let me know, because we can let someone else know, and you can get a job with someone pretty quickly, I'm sure, because that's like talent. But, using our mathematical talent to use the back door, we could say, okay, well the exponential form of this is frustratingly impossible. Let's try the logarithmic form. Log base e of 24,000 is x. And log base e is just our log natural. And you have a log natural button on your calculator. So you do ln, 24,000, and you get x equal to? Does that make sense? Is it going to, like, it took 4.38 copies of 10 multiplied to make 24,000, but it took 10 copies of e multiplied to make 24,000. Does that make sense? E is a smaller number, it's going to take more copies of it to be multiplied to make the same large value. Last way they tend to phrase these, and then we can move on. Let me ask the question, is this making more sense than it made before? Because last time you said you could do it, but not with understanding. Does it seem more understandable? what you end up doing in these problems is you write out what they tell you in mathematical form, and then you're like, I need to be a magician to pull that off. And if you're in an exponential situation and you feel like you need to be a magician, maybe if you went to a logarithmic situation, you wouldn't have to be a magician. It's a possible manipulation. They could work. Just like adding or subtracting something from both sides, you could take something from exponential to logarithmic form. So let's, question?
How would the people back in like the day figure out like calculator?
Tables?
Take a long time.
There would be people who would go through and make tables, and then they would say like e to the 0.1 power is this, and e to the 0.2 power is this, and then you just have a book, and when you needed to look up what this was to make that, you'd go and you'd flip through the book, and then you'd find the number. Do it that way. Yeah. You actually, you may recall in our geometry books, there was a sine, cosine, and tangent table. It was like, I'll even, well, we don't need to get it, you remember. It basically said, 1 degree sine, here's the value. 2 degree sine, here's the value. 3 degree sine, here's the value. Your calculator can do all that, but back in the day, tables. Tables.
That's scary.
Yes, because that was somebody's job. And imagine your whole job every day would be like e to the 0.1. Figure it out, write it down, double check yourself, make sure it's right. Okay, e to the 0.11, write it down. Write 0.0024 as 10 raised to some power. Now we have to take what they give us and translate it into math. Once we do, then we just play math and solve. So I want to write 0.0024 as 10 raised to some power. Can anybody magically intuit the answer? No. So let's try to do something else that's going to get us working in the right direction. Let's try to go to logarithmic form. Log base 10 of 0.0024 is x. Now we have x by itself. And we have a log base 10, which we have a log base 10 button in our calculator. We do log of that, and we'll figure out what x is. And the answer?
Oh, sorry.
Oh, you don't have to apologize.
-2.62.
-2.62, you said that hesitantly. Does this make sense?
Yes.
Yes.
Let's go back here and say 10 to the -2.62 power equals 0.0024. What do we do with negative powers? Move them down to the denominator. So if I had 10 to the 2.62 power in the denominator, I'd have a really, really, really tiny number. And it'd be that number. Makes sense, right? So the fact that we got out a negative is okay, because the number that we were asked to make was a number that was less than 1. And if you're going to have a number that's less than 1, you're going to need a fraction to do it. And to make the fraction with an exponent, you're going to need a negative exponent. Kosher? Sweet. You can put that lesson to rest. let me skip forward for the sake of time, so that we can grab something that's going to be relatively quick to go through. Yeah, let's do something that wasn't done while we had to sub, but something that needs to be done, and this comes from lesson 56. You have some parts of 56, I'm going to add a big part here. And it's called graphing inequalities. Unequal. I say unequal, what do you think? When we're not equal, what kind of mathematical things come to mind? Subtraction could work. I mean, you could kind of think of things unequal like 7 and 2 you could subtract, but when we talk about equality, we talk about this guy. When we talk about inequality, we talk about that guy, that guy, that guy, that guy. Those are all inequality, right? Less than, greater than, that's not equal, that's something different, right? Now, remember back in the day, this would be a nice flashback. Remember when you used to graph inequalities with one variable? One variable requires one number line. So there's the x-axis, right? And then you go out here to 2, and you can be greater than or equal to 2, so you could be 2, that's a possibility. You also could be 2.1 or 2.2 or 2.3 or 3 or 4 or 5 or 10 or infinity for that matter, or anything close to infinity. You're out here. Sound familiar? One variable, one number line. But remember, just like back in algebra, once we introduced 2 variables, we needed 2 number lines. We. Well, the question is, when we've seen 2 variables, all we've really seen is equalities. Why can't we make them inequalities? Like, what's stopping us? Our own imagination, right? So let's just go for it. Now, you know what y equals 2x plus 1 is like. It's a line, right? Now, what if we said y is greater than 2x plus 1? We'll do even better. We'll do greater than or equal to. We'll just say that. Greater than or equal to 2x plus 1. Now, do you know what 2x plus 1 looks like? I hope so. That's y equals mx plus b. Y-intercept. The y-intercept is 1. The slope is 2. So that's 2 over 1. That means rise 2, run 1. We should have a positive slope, so we should be going uphill. And I believe we are. There's our line. Now, the line that I graphed there is y equals 2x plus 1. But what we were asked to do is y is greater than 2x plus 1. So if y is greater, then we're looking for bigger y's. Where do you find big y values? Up, right? Think, look, let me, we normally don't label these because we're so used to just counting off 1, 1, 1. But where do you find the big y values? Up. So where do you find the things that are greater than that line? Up.
Yeah.
Everything above the line. So there's your shape. Now notice, I was careful in saying equal to as well. We can be the line. We also can be everything above the line. If, this is an if, but if it was y is greater than 2x plus 1, we couldn't be the line, we could only be above the line. In that case, when we would graph, we would have to dash the line and then shade. What's above? Does it, Algebra 2 memories? A little bit? Now, here's the nice thing about the way our book does this. The book does the graphing for you. And all you have to do is the shading. Exactly. Exactly. I feel the same way. It's like so, it's just nice. So, let me give you an example of how the book will proceed with problems like this. So, the book will give you this. The book will say, y is greater than or equal to x squared plus 4x plus 2. And in parentheses, they'll say parabola. So you know the parabola is that graph. They'll also say y is less than negative x plus 1, and in parentheses, they'll say line, in case you forgot that lines are like y equals mx plus b. And then, what they will have is a picture of the graphs. And it looks something like this. Here's the parabola, hard shaded. Here's the line, dashed. Make sure my parabola extends all the way up here. So they're already doing work for you, right? Because they're dashing the one that is not equal, they're soliding the one that is equal, and what you will see is you will see letters in different regions of the graph. Because A is this region that's bounded by the dashed line and the two sides of the parabola. C is the region bounded by the dashed line and the bottom of the parabola. D is this region that's down below the dashed line and below the parabola. And B is the region that's above the dashed line and above the, or rather, how should I say this, above the dashed line and outside the parabola. Let's see. Now, we need to be bigger than the parabola. So if the y's are bigger than the parabola, we need to be above the parabola, but we need to be with y's that are lower than the line. So when I look at this greater than, I say I need to be above the parabola. When I see this less than, I say I need to be below the line. So is there anywhere on that picture where I am above the parabola and below the line?
Sure.
So guess what your answer is in these problems? One letter. Sometimes it could take two letters, because there might be two regions that need to be shaded. But in this case, we were asked for our y's to be bigger than the parabola, that means we're above the parabola, and our y's are less than the line, which means our y's are smaller, and we're in region C. I'm going to need to do an additional example of this. The bell's going to ring here in a jiffy, so I'm going to make a note that we need to do an additional example. And the example we're going to do is a circle, because that one's kind of tricky to think about, but it's really not that bad at the same time. And in the meantime, let me send you home with a few things to work on. So, in lesson 56, take a look at 14.